In this video, we're going to take a look at some of the basic properties of limits and seeing how they really lead to direct substitution and seeing how we derive the concept of direct substitution itself. So, diving right in, let's take a look at our first very basic property of limit. And that's going to be the limit of b as x approaches any constant value is going to be equal to that constant b. And the way we get this really is we can think about a graph of this function b. And that function is just going to be a constant function. And a constant function means that we're just going to have a horizontal line. So if we have the example of a constant function, let's say this is 2 units up, so this is going to be y is equal to 2, or f of x is equal to 2. We see that no matter where we approach from, whether we're approaching the value 2 from the right and the left, or if we're approaching negative 3 from the left and the right, we see that we're always going to approach this value b, in this case, which is 2, because the graph itself is just a horizontal line. No matter what we input into the function, the output is always going to be the same, which is that constant value. So because of that, the limit of b, no matter what value we take, it's always going to approach that value b. Now looking at another very basic property of a limit, we have the limit of x as x approaches c is going to be equal to that value x. So looking at, again, at the graph of this particular function, let's draw the graph right here. The function for this is going to be right here, which is y is equal to x, or f of x is equal to x. And that's just going to be our basic line with a slope of 1. So the rise and the run is going to be equal. So what does that really mean for us, though, if the slope is equal to 1? It basically means that the x and y coordinate for every single point on this line is going to be exactly the same. So we have 1, 1, 2, 2, and if we wanted to get even smaller, we can have half and half. And every single value on this line, the x and y coordinate are going to be exactly the same. So when we look at the limit, and we're trying to see what y value are we approaching when we have a particular x value. So if we pick, let's say, 2, we're going to be looking at where the graph approaches from both sides as we get closer and closer to 2. And since we know that the x and y coordinates are going to be exactly the same for any given point on this particular graph, we know that if we pick any value to input into x, the output is going to be the exact same value as that. So because of that, if we want to look at where the graph approaches when we pick a value such as 2, we know that it's going to approach the value of 2 as well for the y coordinate. So using these two properties, we want to eventually use the next properties we're going to take a look at to eventually break down any function into these two basic properties so that we can directly substitute in that. And this is how we get direct substitution. So if you don't quite understand that yet, let's take a look at our properties first and we'll do an example. So now we can take a look at some of the more complex properties. So the first one we're going to study is the scalar multiple property. And what the scalar multiple says that if we have a limit as x approaches c times, the limit of b times a function, we can basically split that and move this b over to the front over here, and we can have the b times the limit of f of x. So we're basically just taking this constant that we're multiplying the function with and take it out all the way in the front of the limit. So we just have the limit of f of x times b instead of the limit of b times f of x. The next property we're going to look at is the sum and difference property. So sum and difference property. And what this tells us is that if we have the limit of something that is added together, so f of x plus or minus g of x, that's basically, we can kind of think of it like you're going to distribute this limit over, and what you essentially get is we get two different limit kind of chunks. So we have the limit of f of x plus or minus the limit of g of x. So basically, if you want to think of it this way, we're kind of just distributing this limit over to these two different functions, so we can take the limit of each function separately and then add or subtract the result. The next property is slightly similar to the one we just studied. That's just going to be the product property. And what that does is essentially we're just going to be distributing again, but this time instead of it being that we're adding or subtracting these two functions, we're going to be multiplying these two functions. So as you might have already guessed, we're going to split it up again into the limit of the first function, in this case f of x, and then we're going to multiply that by the limit of g of x. So again, we're going to be distributing this limit into these two functions here. So I note here we're just basically distributing. Alright, so now we just looked at product, so let's take a look at quotient. And again, this is very, very similar to the last couple we did. So I'll bring this down here as well. But basically we have the limit of f of x over g of x, so we can make that into the limit of f of x over the limit of g of x, x as x approaches c over here. So again, we're not really distributing here, but we're just going to apply this limit to the numerator and the denominator, so we're taking the limit of the two separate functions. So now, finally, we have the power product. When we're taking a limit to a certain power. And basically what we can do is if we have the limit as x approaches c of f of x, and we're taking this limit to the nth power, we can bring this limit, this power over and apply it to the limit as well. So we're going to have the limit of f of x whole. We can take this entire thing to the nth power and vice versa. Okay, so these are basically just our 5 main properties, and what we want to try to do in any given problem is we want to use these 5 properties and simplify an expression, or a function down to these 2 basic properties so that we can apply direct substitution. So this is kind of how we derive direct substitution. So let's take a look at an example. So we want to find the limit using the properties of this function that's given to us. So 3x cubed minus 2x squared. So the first thing we can do is we can split this up into the, we can use our subtraction property, and we can apply this limit over to these 2 functions here. So we get the limit of, as x approaches c, of 3x cubed minus the limit as x approaches c of 2x squared. And now what we can do is we can use the scalar property and move these 2 coefficients out to the front. So we get the 3 times the limit of x cubed minus 2 times the limit of x squared. And now we can get rid of this power as well. So what we can do is, we'll move it down here. What we can do is we can, since we can take the cube of this entire limit over here. So instead of the power exponent being on just the x, we can have it on the entire limit. So that'll essentially give us this basic product, the limit of x as x approaches c, which we know is just equal to x. So basically just showing the work here, we'll have the limit of x cubed minus 2 times the limit squared. So now since we have this basic unit right here, since we have this basic unit right here, if we move back up, we basically just have this property right here. We have this property right here, a very basic property. The limit of x as x approaches c is just equal to x. So we can use that property and we can replace the x value right here. And in this case, we want to find the limit as x approaches 2. So what we're doing is we'll replace this with 2. We'll replace this with 2. So we have 3 times 2 cubed minus 2 times 2 squared. And if you notice, this is exactly what we do when we have direct substitution. We have the function 3x cubed minus 2x squared, and we're just replacing every instance we see x with 2, which is what we're trying to find the limit of. So this is basically just our process, or the long way of showing why we can use direct substitution. We use all of these properties to essentially break down this function so that we have our basic unit limit of x as x approaches c, which we can replace with the x value we're trying to find, in this case 2. And that's how we get direct substitution. So if we just simplify this, 2 cubed is 8, so 3 times 8 minus 2 times 4 is equal to just 24 minus 8, which is equal to 16.